Since younger galaxies have spiral structure and older ones elliptical, we can draw the conclusion that galaxies evolve from spiral into elliptical ones, and eventually all of them will end up having the same spherical shape as planets and stars. Considering fractal distribution of matter in the universe, the similarity between different scale material structures such as atoms and solar systems, stars and elliptical galaxies, and also taking into account the fact that atoms formed much earlier than solar systems and stars formed much earlier than elliptical galaxies, we can assume that our universe is a fractal that is being built from the infinitely small scales towards the infinitely big. Since we are part of this fractal and fractals have the property of self-similarity, we can also assume that on the smaller scales and more precisely on the surface of electrons, there might exist a much older, much larger and much more evolved civilization of similar to us intelligent beings. If it's true, then maybe the order that we see on the smaller scales, like the periodic table of elements and laws of chemistry and physics, is nothing else but standards on inhabited planetary systems and rules on the interactions between them. And if it really is so, then God is an infinitely layered collective intelligence, kind of like a Russian doll, if every doll represented the collective intelligence of a specific scale level. The biggest doll in this metaphor would then represent our own collective intelligence, at least in the visible part of the universe.
What I'm about to show you is one of the most remarkable mathematical images ever discovered. Epic doesn't really do it justice. This is the Mandelbrot set. It's been called the thumbprint of God, and when we begin to explore it, you'll understand why. Just as with the tree or the broccoli, the closer you study this picture, the more detail you see. Each shape within the set contains an infinite number of smaller shapes, baby Mandelbrots that go on forever. Yet all this complexity stems from just one incredibly simple equation. This equation has a very important property. It feeds back on itself. Like a video loop, each output becomes the input for the next go. This feedback means that an incredibly simple mathematical equation can produce a picture of infinite complexity. The really fascinating thing is that the Mandelbrot set isn't just a bizarre mathematical quirk. Its fractal property of being similar at all scales mirrors a fundamental ordering principle in nature.
So the main problem with this idea is that it requires two infinities, an infinitely big universe or the infinitely big, and an infinitely divisible matter or the infinitely small. But the scientific community doesn't always welcome infinities.
You get something which makes no sense whatsoever. An infinity. Total nonsense. To a mathematician, infinity is simply a number without limit. To a physicist, it's a monstrosity. In the real world, there's no such thing as infinity.
In fact, infinity gives them such a headache that throughout history natural philosophers and scientists always try to limit the two infinities.
What made the idea of infinity so troubling to the Greeks is that it clashed with their goal of using numbers to explain the workings of the real world. To preserve the idea of a limited universe, Aristotle would craft an historic distinction. On the one hand, Aristotle pointed to the irrational numbers such as pi. Each new calculation results in an additional digit, but the final number in the string can never be specified. So Aristotle called it potentially infinite. Then there's the actually infinite, like the total number of points or subdivisions along a line. It's literally uncountable. Aristotle reserved the status of actually infinite for the so-called prime mover that created the world and is beyond our capacity to understand. It was Aristotle's ideas that passed into the Christian era, along with his cosmology, with Earth seated firmly at the center. That view was not universal. Islamic, Hindu, and even some Western thinkers posed alternate views that included infinite space. In European circles, the issue of infinity resurfaced during the Renaissance. In 1543, the Polish astronomer Nicholas Copernicus argued that Earth orbits the Sun, not the other way around. The old Greek spheres began to fall by the wayside when a distant supernova, then a comet, were spotted by the astronomer Tycho Brahe. These objects seemed to behave independently of the other stars. A monk named Giordano Bruno inflamed the issue by traveling Europe at the height of the Inquisition to proclaim an infinite universe. In the year 1600, he was burned at the stake for this and other heresies. Just 9 years later, in 1609, Galileo Galilei used the first astronomical telescope to show that the universe is much larger than we thought. In later writings, he even sought to discredit the distinction between potential and actual infinity. Galileo was forced to recant, and the old Aristotelian view held sway. Any attempt to assign a value to infinity, in numbers or in nature, was doomed, for that was the unique province of God. Finally, at the end of the 19th century, the mathematician Georg Cantor sought once and for all to divorce metaphysics from the abstract pursuit of math. Infinity, he wrote, had to be studied without arbitrariness and prejudice.
Well, infinity was always there, but they tried to contain it. They tried to keep it in a cage. And people would talk about potential infinity, not as opposed to actual infinity. But Cantor just goes all the way. He just goes totally berserk.
What was inspiring for Cantor frightened his critics. They saw mathematics as the pursuit of clarity and certainty. Everything Cantor was doing, his irrational numbers and his illogical infinities, seemed to them to be eating away at certainty. He soon faced a deep and implacable hostility.
Even as mathematicians embraced infinity, astronomers in the early 20th century still saw a limited universe, centered on the galaxy, a flat disk of stars. Did the limits of our vision, like the horizon at sea, conceal an infinite universe beyond? Albert Einstein, for one, believed that if that were true, then the night sky would be filled with dense starlight shining from every direction. We'd reel from the effects of infinite gravity. Arguing for a finite universe, he described a people living on the 2D surface of a sphere. To them, a beam of light moving through space would appear to go straight on an infinite journey. In fact, it follows a path determined by the overall gravity of the universe and curves back around. Like the old Greek spheres, this view of a static and limited universe began to fall by the wayside in the 1920s. Edwin Hubble and Milt Humason used the new 100-inch telescope on Mount Wilson in California to look at mysterious fuzzy patches of sky called nebulae. They found that these patches were galaxies like our own, and that some were very far away. What's more, they found that most are moving away from us. The farther out they looked, the faster the galaxies are moving. This fact, known as Hubble's law, led to an inescapable conclusion that the universe is expanding.
If the universe were positively curved, if the angles inside the triangle added up to greater than 180 degrees, then it would be finite in size. If the spatial geometry is flat, if the angles inside the triangle add up to 180, then it could go on forever.
The result is one of the greatest triumphs of modern cosmology. A miracle of precision map-making that measures the angles of the triangle to the third decimal place. And it says that the universe is infinite.
The answer is that Euclid was right. Space seems to us to be flat as far as we can measure.
That means that the simplest picture of the universe is a universe that's infinite. We really could live in a universe where there's galaxy after galaxy after galaxy in every direction, up, down, sideways, and it never stops.
So the infinitely big prevailed. What about the infinitely small?
I had the great privilege of having a discussion with the famous cosmologist Stephen Hawking when I passed through London recently. And I said to Dr. Hawking, the Mandelbrot set is infinite in detail. You can explore it forever and ever, zoom into it. The real universe, however, does seem to have limits. As you go down to the micro world, you get, of course, molecules, atoms, neutrons, and perhaps subatomic particles, quarks. But does the real universe go on forever? Is there a limit, a basement, unlike the Mandelbrot set?
In the case of the universe, there seems to be a limiting scale. It is called the Planck length, and it's about 1,000,000 billion times smaller than an inch. This means that there is a limit to how complex the universe can be. It also means that the universe could be described by a theory that is fairly simple, at least on scales of the Planck length. I just hope that we are smart enough to find it.
He thinks that there is a limit in the real universe. There's a small size below which nothing exists, called the Planck length, which is about 1,000,000,000,000,000,000,000 of a centimeter. Unimaginably small, but that is the fundamental unit of size, the sort of grittiness of the universe. Nothing smaller than that. So perhaps the real universe does end there in smallness, but we're not sure. It may indeed go on forever, like the Mandelbrot set. We just don't know yet.
But why did they really try to limit the infinitely small?
In essence, by the beginning of the 20th century, scientists saw the universe as a giant, complicated mechanical device. Kind of a supersized version of this orrery. The idea was that the universe is a huge and intricate machine that obeys orderly mathematical rules. If you knew the rules of how the machine was configured to start with, as you turn the handle over and over again, it will behave in an entirely predictable way.
Back in the times of Isaac Newton, when people were discovering the laws that drove the universe, they came up with this kind of metaphor of a clockwork universe. The universe looked like a machine which had been set going at the instant of creation and just followed the rules and ticked along. And it was a complicated machine, and therefore complicated things happened. But once you set it going, it would only do one thing. And the message that people drew from this was that anything describable by mathematical rules must actually basically be fairly simple.
This means that there is a limit to how complex the universe can be. It also means that the universe could be described by a theory that is fairly simple, at least on scales of the Planck length.
Find the mathematics that describes a system, and you can then predict how that system will unfold. That was the big idea.
It began with Newton's law of gravity, which can be used to predict how a planet moves around the sun. Scientists soon found many other equations just like it. Newtonian physics seemed like the ultimate crystal ball. It held up the tantalizing possibility that the future could in principle be known. The more careful your measurements are today, the better you can predict what will happen tomorrow.
But the Newtonian dream of a totally predictable universe died anyway.
During the second half of the 20th century, a devil was found in the detail. A devil that would ultimately shatter the Newtonian dream. Chaos is one of the most overused words in English, but in science it has a very specific meaning. It says that a system that is completely described by mathematical equations is more than capable of being unpredictable without any outside interference whatsoever.
It says some very, very simple rules or equations with nothing random in them, they're completely determined, we know everything about the rule, can have outcomes that are entirely unpredictable.
Chaos is one of the most unwelcome discoveries in science.
So now that the dream of a totally predictable universe is dead, why are we still looking for the fundamental building blocks of matter, even when we've previously been shown again and again by nature that beneath any given layer there's another?
These machines have revealed a whole array of particles which, we believe, may be the fundamental building blocks of matter. But back in the 19th century, scientists thought that everything on Earth was made of just over 80 elements.
But there's another big problem with the idea of a fractal universe. According to quantum physics, the atom is not exactly like a solar system. Well, imagine a caveman that for some reason stumbles upon a miniature modern city. Small enough for him not to see the people, but big enough for him to see the vehicles. Will the caveman see that the buildings are basically artificial mountains with multiple caves in them? And will he see that the vehicles are basically artificial horses that he might already thought about using as transportation? Probably not, but what he will see is order. He will see the use of standardized shapes and sizes, like the rectangular shape used in most buildings and the height of a single floor. But since he cannot anticipate that such order can be created by a legion of his descendants, he probably won't see the resemblance. And that's exactly what we see when we look at the smaller scales. We see order. And just like for the caveman, it's hard for us to anticipate how future artificial standardized planetary systems might behave or look like.
Bhor described the atom not as a solar system, but as a multi-story building. The ground floor is where the nucleus lives, with the electrons occupying the floors above. Mysterious laws mean the electrons can only live on the floors, never in between. And other mysterious laws mean that sometimes they can instantaneously jump from one floor to another. These are what we call quantum jumps.